So WA Array, it's a new statewide passive seismic data set. I'm sure you're all familiar with other statewide data sets that the survey have, like the gravity, the magnetics. What we're going to now is passive seismic data. So I'd like to tell you what this will hopefully do for you very shortly. So we know about the rationale. We're trying to go undercover, looking for mines, which are currently undercover. And this is to feed the new zero carbon economy. We know why we're chasing these minerals. I'm going to come back to this map. As Fauna said, a lot of this map has been made without appropriate number of data points within Western Australia. And we are chasing that steepest gradient within the LAB, the lithosphere-asthenosphere boundary. So that's the whole goal of this. We're looking for junctions between the cratonic blocks for big mantle-tapping structures whereby fluids can come up to the surface and produce deposits. So how are we going to look that deep? We're looking 100 or more kilometers down. The standard geophysical techniques we're using at the minute are not going to get that far down. Passive seismic is one of those globally useful technologies, and magnetotellurics as well can, if you're using the right equipment, see that far down. So we're looking at below the crustal levels in some of this stuff. What work has been done in Australia up to now? The passive seismic data, as you can see, that was before this project started, is a bit patchy. There's great blank areas. The Oz lamp, as you'll see, most of the eastern states have got a good covering, but as usual, in Western Australia, if you want to do it, we'll do it ourselves. So we're very grateful to the Western Australian government for supporting these two projects because it was not going to come out of federal. So this is the map that I'm working off. Every spot, every grey spot on that map will have a passive seismic survey completed at it and a magnetotelluric survey. There's 1,500 points there. It's going to take us a while. Some of those places are pretty remote. So as Rose said, we're going to take soil samples. We're digging a hole to put our seismometer underground. We're taking the soil sample to send back to Rose's team to do geochemical, geochronology analysis, any other analysis we can on that sample. So there's the passive seismic, the MT, site characterization. This is another passive seismic technique, but it's looking very shallow. It looks a bit remote, a bit esoteric out in the remoter areas, but certainly in the first area we've been looking at is fairly applicable, dealing with seismic hazard and more building technology, engineering information. 1,500 points. We're not going to do that all at once. We're going to do it in 9 regions. Basically, we've divided it up into 9 regions. This was the ideal map that we started out with. Changes every day. What we have completed is the southwest. And you'll notice that around the southwest is the green area, the eastern goldfields. That data will be coming out next year. And I hope this time next year, our team will be standing up and telling you about what we found out from that. So that's going to be really exciting. But just to whet your appetite, I'll show you some of the things we've been getting out of the data set from the southwest. So I'm afraid if your tenements are somewhere other than those two, you're going to have to wait a few years, but we will get there. Phase 1, we're calling it. Phase 1 was down in the southwest. On the top, you'll see the spots that we managed to deploy our seismometers. This was 167 new sites. This went in the ground in late September 2022 and was taken out in December 2023. And we released our data set a year later. We are committing to release the data sets, not the full tectonic interpretation, just the data set, so you can go away, put it in your own models, see how it fits. We're committing to release that data set a year after it comes out of the ground. So that's why I'm saying this time next year, we will see the stuff from phase 2. If you have a seismologist who's really into dealing with seismic squiggles or the MT data, the seismic data will go up through OzPass, and the MT data is available through Magix. So you can play with the raw data if you really want to. The models are also, the derived models, and I'll show you some examples of those, are also available through the Magix website. The Magix website is the GSWA's geophysical database. So the report for phase 1 is coming out imminently. This is a list of some of the products. And basically, it's always going to work from the shallow down to the deepest. Site characterization, some of those engineering parameters that are really useful when you're designing big infrastructure, when you're looking at seismic hazard. Local earthquakes, particularly useful in the southwest. We can get crustal models of the VP and the VS values. Why is that useful for geologists? It's going to, the differences, different blocks of different velocities are going to tell you sort of about more the crustal structure, the big crustal structure. Ambient noise tomography in the crust, again, this gives us a velocity structure in the crust. Depth to MOHO, changes, different cratonic areas, different geological areas may have different depths to MOHO. This is going to help us with the history and the cratonization of Western Australia. Some of the splitting directions, I'll tell you a bit more about shear wave splitting as we get on there. P-wave mantle tomography, we're going to do the P-wave structure in the mantle as well, and surface wave tomography, which is giving us the S-wave structure in the mantle, and this will give us the depth to the LAB as well. There's a lot of stuff in there, and you can see we have a lot of collaborators helping us out with this data set. Earthquakes. How many do we get in Western Australia? Quite a few. If you guys have worked around Kalgoorlie, you know there's always the question, do you get earthquakes in Kalgoorlie? I'm not going to answer that question today. In the southwest, where we've been doing our work this time, there is a lot of natural seismicity as well. It's just one of those areas, it's intraplate seismicity. We don't really know why it's going on, but we're hoping to characterize that better. However, a lot of the earthquakes we're actually using are teleseismic earthquakes. Over there's a nice picture. I don't know if people have been aware, we've been having a earthquake swarm in Arthur River, started in January 2022, 23. And that's an example of actually one of the third main shock, 4.1. And this is just a time series, it's about an hour a time. 24 hours later, the Turkey earthquake happened. So you can see the sort of size, these are the surface waves. You can see the size, the amplitude of the surface waves compared to a local magnitude 4. So we are using that data from teleseismic earthquakes, and here's a map of some of the earthquakes that we were using in our analyses all around the sort of Circum-Pacific, around the Indonesia, New Zealand area. This is the data we're using. So even though Australia itself is not particularly seismic active when you're looking at telesis like that, we can use that data as it comes up from underneath our feet to imply the structures below us. And some of these, like this is actually the Narangrup. We've had a little window rattlers at Narangrup. We use the direct waves. These we call the body waves. We're also using stuff that's come right through the core, bounced off various places along the way. All those different phases take different times to arrive, and we can use that difference to work out the structures below us. Let's start with the shallow stuff. The site characterization. Different sized buildings react to different frequency of waves coming through the ground. So we need to know what sort of the fundamental frequency of that bit of ground if we're going to build big infrastructure. I mean, some of the obvious big infrastructure which suffers from earthquakes was the pipeline, which suffered during the Meckering earthquake, completely shunted into itself. This sort of information is good for new big structure coming up. We're using a little geophone like so, which we bury in the ground. We can use it in an array, and this will give us shallow level velocity structures. And these are the sort of maps we're getting out of it. Depth to engineering bedrock, depth to geological bedrock. Those are both defined on the specific seismic velocities. We got a fundamental frequency. We get the velocity in the top 30 meters of sediments. So I know it's quite sparse, 40 kilometers, when you talk about an engineering thing. Hopefully you don't have that many engineering projects 40 kilometers wide, but when we put it on the map of the tectonic, the structures in this area, it's fitting in quite well. And we can lay that again on sort of the Paleo Valleys maps and that sort of thing. We can relate some of these sparser measurements, and they do relate to the geological features we are aware of. Obviously, if we were going to do a big project, we'd do this in much more detail. But it's just a base map to start with. Local earthquakes. This is all the seismic events that we recorded. There's over 4,000 in there. As you can see, a lot of them sit right on top of mine sites. These are actually mine blasts. And we know about that. We know there's a mine there. That's not a problem. However, all the blue circles are natural swarms. These are the swarms which have happened in the past 3 years in southwest Western Australia. What type of earthquakes are they? They're all east-west compression events. So that's really interesting. The motion of Australia is more northwards. So why are we getting compression here? We still don't actually know. We got so many events there that we can actually use a tomographic method between stations and events to work out velocity structures, the P wave, the S wave. We also use the ratio of the P to S wave to work out what type, or how mafic the rock is in these areas. So these maps are all available. Okay, one of the big questions, one of the things we've been hunting for years is the depth to Moho, because that tells us about the different cratonic blocks. We're going to use the differences between an incoming wave. As it goes through the Moho, it will either split into an S wave and a P wave. It may go straight through as a P wave. It will bounce off the surface, come down, back up to the station. And at any of those interfaces, it could have a mode conversion to S waves. S waves travel slower than P waves. So these differences in times gives us the different lumps and bumps of our seismic signal. This is data actually from a ray we ran several years ago up in the Gascoyne. You can tell the main Moho reflection, the direct P wave, and these are some of your secondary bounces coming off. The differences between it, we can work out the depth to Moho from those. So in the southwest, we can have this map of the depth to Moho. You can see the basic tectonic features, and obviously we've got a tectonic feature going across here, the depth to Moho, which doesn't quite fit in with our map structures. So that's something we've got to work out what's going on there. We can see the difference in the Perth Basin, we can see the difference in the Albany-Fraser around the bottom, but there's something going on in the crustal levels with the Moho. And on the far side, you can see the VP-VS ratio. Again, we've got differences to the south in the Yilgarn as opposed to in the north. We can see the Perth Basin here, Albany-Fraser, not quite so different. Again, we could start making some tectonic interpretations. Ambient noise. So far, we've been using earthquakes. A lot of the time, there's nothing going on. The Earth's just sitting there, just humming away. We can use that noise to work out velocity models, again, of your S wave in the crust. If we're really interested in how you do it, our expert is sitting here while he's done all this work, so if you want to know how we do it, he can explain it for you. So splitting, I had this picture up earlier. These are teleseismic waves that have come through the center of the Earth, and through the core, they've lost any source, any signal imparted by the source end, so we're only looking at the receiver end of the splitting. And as the surface wave comes in, it splits into a fast direction and a slow direction, which, depending on the strength of the anisotropy in this area, is smaller or lower, and the amplitude of the splitting is greater or less. We've managed to extract a number of splitting measurements across the Yilgarn, or the western Yilgarn, and again, you can see the vector of motion up there is almost perpendicular to this. So we reckon that is frozen in. This is a frozen anisotropy which is deep within the lithosphere. So it's probably, it's showing a deeper crustal frozen in route there. P-wave mantle tomography. We're seeing the difference in the perturbed areas. You can see that where the origins have gone through. A more pristine, deep mantle signature. A stable mantle signature is coming in the middle of the U&Me terrain. Surface wave tomography. This is a series of seismograms coming in from an example event up here, and this is our ray. You can see the initial P wave, the S wave, and then here come the surface waves. If we take one station and we split it into its different components, different frequency bands, higher frequency looks at the shallower, and when we get down to the low frequency, the really long wavelength signal, we're looking really deep down into the Earth. So a lot of the work so far done in the rest of Australia has not used this really broadband stuff, and we're one of the first groups to actually image this far down. What do we get? 80 kilometres, we're getting this solid route in the underneath the craton. We can see the lower velocities again around the edges, although somehow that seems to be slurping out into the Pinjarra origin this way, and then the Albany-Fraser coming round. Deeper down, we see this more concentrated route in the Yuan terrain. And I think this is one of our prized pictures. This is actually the shape of the lithosphere-asthenosphere boundary. We've been seeing this route. This contour about here is actually the steepest gradient, which is the one I showed you right at the original Hogarth slide. And we've redefined it in this area. And then we put the gold deposits on top of it. It's quite a nice match, really, isn't it? So we're pretty pleased with that. Obviously, there's a long way to go. We've got to cover the rest of the Yilgarn before we really start crowing about it. But we've proved we can image that far down, and there seems to be a direct correlation with the deposits in the area. Magnetotellurics. This again shows we're doing long period magnetotellurics. We're basically looking from the MOHO downwards. People ask, why aren't we doing broadband? And that's a technical reason. And the dimensionality of the Yilgarn is definitely 3 dimensions, which means you really need a near neighbor to help the processing. And 40 kilometers is too broad for that. So that's why we're doing the deep stuff only. We haven't really got enough data to say too much about it. Hopefully by the time we have phase 2, we can integrate the rest of phase 1 with it. That's still work in progress. So, as I said, we haven't done the full tectonic model. Yes, it's not part of our remit as this project. The main thing is to get the data out to you, and you can work on the tectonic models yourselves. We as a survey obviously are doing that, and I think some talks later today will be touching on the work that we have been doing in building the full tectonic model. But the things to note, the shallow crustal features seem to reflect the tectonic environments of today. No big surprise. Crustal models, these seem to be different. These seem to have the sort of northwest to southeast trend across the bottom of them. So we have a bit more work to do on that. However, once we get down into the mantle models, we're seeing this lithospheric route under the Yuan terrain, and that fits more with the surface tectonics that we see. And the gold deposits seem to lie along those trends. There is a 3D data compilation in GSWA GoCAD or Geoscience Analyst that is available through Magix. The report, as I say, should be out any minute. OzPass, if you want the raw data, Magix, if you want the models, and the report will come through our e-bookshop with the usual ways of finding any of that data. Where are we going? So this is the bit that interests you. We have finished phase 1. As you can see, I'm here in my work clothes. We have literally been grubbing around in the dirt, pulling out phase 2 right now. And it will take us a year to do the data processing. As you can see, we're building this block around that, so it'll be a big Goldfields Yilgarn project next year, and hopefully this time next year we'll be able to tell you lots more about our results.